all of mine. Sorry? Yes, only one-sided, single-sided, handwritten. I feel like that would be. You should just spend your time learning the material instead of finding loopholes. Okay, so the things that we need to know here are we need to know for how many torrs in atmosphere. So let me look up in Alex. Oh. Conversion factors for non-SI units. So we need to know some of these. So 1 atmosphere is, we need to know torr and millimeters of mercury. 1 torr is 760 millimeters of mercury. And, 1 atmosphere. Oh my goodness. 1 atmosphere. There you go. I'm getting them all mixed up. 1 atmosphere is also 760 torr. Okay, so this also tells us 1 torr is 1 millimeter of mercury. So the vapor pressure of methanol is 126 torr. Calculate in millimeters of mercury in atmospheres. So if it's in torr, it's already in millimeters of mercury. So we can just say 126. Remember, we're getting our sig figs from this value. So this has this one has 3 sig figs, so our value should have 3 sig figs. The next one is atmosphere, so I'm going to start with the number in torr. I got it in 126 torr. And I need to convert that to atmospheres. So the unit that I'm trying to get to needs to go on the top. So that's here. Oh, let's see. Let's use that one. 1 atmosphere is the same as 760 torr. Torr cancels out, we end up with atmospheres, and then we just do this on our calculator. You can use the Alex calculator or your own calculator. 126 divided by 760. And we need 3 sig figs, 0.16, and I'm going to round up to a 6. 0. Oops. Okay, and that's in atmospheres. Okay, so not too bad if you know how to convert. Do you have, I was like thinking maybe you had like a different one that you wanted to look at. Okay, let's just keep going through. We have spent some time on that one already, so let's do, the next one is Boyle's Law. When you see these on the test, they won't say Boyle's Law. So what I like to do is I like to look at this. Oh, it's a cylinder problem. So how do I do the cylinder problem? Did you guys like the table method, or did you like just the equation method? The equation method? Okay. The equation method is, we can try, yes. So for the piston problem, so that means you have a picture of a piston. So I'm going to draw my beautiful piston, okay? You have P1V1 equals P2V2, okay? So it's a proportion problem. All right. So think about what's happening. If you increase the pressure on this piston, what's going to happen to the volume? The volume's going to go down. So think intuitively, you know what's going to happen, okay? What if you pull the piston up? What's going to happen to the volume's going to increase, the pressure is going to decrease, okay? So make sure that your values are matching what you already know should happen, okay? All right, so if we're doing just the equation way, we look at what we have. So volume 1 is 10 liters. The initial pressure, so P1, is 290 kPa. Final volume, 3.4. Volume 2 is 3.4 liters. Okay, so what happened to our volume? It went down kind of a lot. So what should we expect our pressure to do? It should go up. Good. So pressure should go up with volume going down. Okay, so we can just make sure that happens, all right? So I'm going to plug in my values, 290 kPa. Oh, I'm not going to have enough space. Let me put it down here. 290 kPa times 10 liters equals P2 times 3.40 liters. I'm going to divide both sides by the volume. Then P2 ends up there, and liters cancels out. We have a pressure unit. That's great. And then we just plug that into our calculator. So we're changing our initial pressure times by this ratio, 10 divided by 3.4. All right, and then we need to check, we expected our pressure to go up. Did it go up? Yes. And also we need to look at the numbers in the question. Practice figuring out sig figs. 3, 3, 3, so our answer should have 3. There's a 9 here, so I gotta round that up. 853 decimal. Okay. Do you want to do the other way, the table way?
Sure.
Okay. So the table way is we are thinking about all of the variables in the P, V, N, T, P, V, T. Okay. So here, the number of molecules doesn't change, and the temperature doesn't change. Those are constants. But here, so this is our initial, this is our final, and then this is what we expect to happen. So initially, the pressure is at 287. Oh, that's 07, sorry. Volume is at, I almost need to be like in 2 spots. 10. Oh, we had 10 liters. And the final volume is 88 liters. Oh, it got a lot bigger. Okay, so the volume is increasing. So if the volume of our piston increases, what can happen to the pressure? It's the opposite. This one's opposite. So if you're making your syringe bigger, then it's creating a vacuum. Your pressure is decreasing. So this should decrease. So then we just take the pressure value, 287 kPa, and then make it, with this ratio, a ratio here, make it go down. So what ratio of the volumes, what number of the volume needs to go on the top to make this go down? Oh, so which one of these numbers needs to go on the top to make the pressure go down? 10. And then 88 goes on the bottom. Liters cancels out. We end up with the pressure value. Pressure is going down. Oh, come here, calculator. Okay, we've got 287 times by this ratio, 10 divided by 88. And that will decrease our pressure. So we just have to make sure 3 sig figs, 3 sig figs, 3 sig figs. So our value will have 3 sig figs, so 32.6. Okay, so that's the 2 ways to do that problem. The next one is Charles' law. So again, it won't tell you that it's Charles' law, so you have to identify Charles' law. Okay, this one's the balloon problem. So Arctic balloon. So we just have the table up. Let's do the table again. PVNT. Let's make it a little bit bigger. So where did we start? Where did we end? What do we expect to happen? So this one is an initial volume. So our volume is going to change. So we initially have 43.1 as our volume. And then we also have temperature. We fill the balloon and then we don't change the number of moles. And then it's in the same place. It's just atmospheric pressure. The pressure is going to stay constant. Okay, so our volume and our temperature are changing. Oops. So this one, we need the temperature to be in Kelvin. Okay, not always do we need that, but for this problem, the temperature has to be in Kelvin. So we need to remember how to convert to Kelvin. So do you remember how to do that? 273.1. Good. Plus our degrees Celsius gives us Kelvin. Okay. So 7. The first one is 7. So 273.15 plus 7. This has no decimal places, so our answer can have no decimal places. So this is going to be 280. Do you agree with that? Okay, Kelvin. And that's our initial temperature, 280. All right, the final temperature, we take the balloon outside and it goes down. So 273.15 minus 19. I don't know that. My calculator is going to tell me 273. Oh, thank you. 273 minus 19 gives us 254, no decimal places. So these both have 3 sig figs. So we check the sig figs once it's in Kelvin. So now these both have 3 sig figs. So we're going to look at all the other values, but that's how we're getting 3 sig figs. Okay, that's something that's been confusing in past years to students. They can't figure out how many sig figs. They think it's 1. It's not 1. It's 3 because now it's in Kelvin. Now this has no decimals. It has 3 sig figs. Okay, great. 254 is our final temperature. So remember back to that video of the balloon, or maybe you've experienced, you've seen a balloon shrink or grow because of the temperature. So what happens to the volume here if the temperature will go down? It should also go down. The balloon, our Arctic balloon, should decrease in volume. So we're going to do the same thing that we did before. So we have this value. We're going to take that value. This is our initial volume. And then we need to use these numbers to make the volume go down because our temperature is going down. So what number needs to go on the top of this ratio to make the volume go down? The final temperature, 254, 280. So then this ratio will make us have the correct smaller volume based on the ratio of the temperatures. Okay, so 43.1 times by this ratio, 254 divided by 280. So this process is right. Hopefully my numbers are keeping track of my numbers. And then remember our temperatures now have 3, our volume has 3, so this should have 3 significant digits. 39.1. Okay. All right. Yes. Arctic balloon equation weight is, I have it up here. The Arctic balloon is V1 over T1 is equal to V2 over T2. So we just have to figure out what we have. So initial volume, I'm just going to replace this. Initial volume is 34.1 liters. We're going to be looking for the final volume. What's going on over there? Okay. All right. Okay, so 273 plus 9. That's our initial temperature. I'm putting in Kelvin. This is going to have 3 sig figs. Is this 12? 282. Is that right? And then this one the temperature goes down again. I think we decided it always goes down, but sometimes it can stay the same. So watch out for that. 273 minus 27. I don't know that one, so my calculator is going to do that for me. 273.15 minus 27. We can keep no decimal places. 246, no decimal places. Both of these have 3 sig figs. All of my numbers do, so my answer has 3 sig figs. And then I have to solve for volume 2. So I'm going to just multiply by the volume. And then I have volume 2. So let's put that in. So 246 times by 34.1 divided by 282. Oh! Just undo. Okay, so then my value needs 3 sig figs because of the values in the question. Just double check that. A lot of the homework topics just are the same all the time. But occasionally the test questions, they throw something different in. So just be awake when you're taking the test. Always double check the sig figs, yes. Okay, so that is called Charles' Law or Arctic balloon problem. Okay, next one is Avogadro's law. So this one has some tricky problems. There's quite a few different types of this problem. Here it is. So this one is the only way I know how to do this type is to use the ideal. Oh wait, is this one? Okay, this is a different one I'm thinking. Okay, so this one you have to write the equation. So this one, we have methane. This is where you're going to have to start knowing the chemicals. So make sure you're ready for that. So methane, do you guys know what methane is? Methane is CH4. So also remember, like oxygen. When they say oxygen, they mean O2. When they say fluorine gas, they mean F2, or chlorine gas is Cl2, okay? Hydrogen, H2, good. What else? We have like nitrogen monoxide would be NO. Nitrogen dioxide, okay? You're going to have to start recognizing these names. Do you feel pretty comfortable with those? Okay, great. Okay, what is tetra? Something... 4. Tetra is 4. Sometimes people get stuck on that, and I can't tell you on the test, so I'm telling you now. Tetra is 4. Okay, methane gas and oxygen react to form water. Methane gas, so we just talked about methane gas and oxygen react to form carbon dioxide and water. Water. I know what water is, carbon dioxide. Okay, so the first thing that we have to do is balance. So carbons are balanced already. Hydrogens, we have 4 here and 2 here. So I'm going to put a 2 here. So now I got 4 and 4. And then oxygen, we've got 2 and 2, that's 4. So I just have to have a 2 here. Okay, so this type of problem, the first thing I need to do is write out the equation and balance it. Okay, and then this one is like the mole to mole problem, but with volume. So it says, what volume of water? So I'm going to write that down. What am I looking for? I'm looking for water. How much volume of water would be produced by this reaction if 6.04 liters of methane were consumed? So the chemical equation is relating how many moles of methane to how many moles of water. 1 mole of methane for 2 moles of water. So if I start with using up 6.04 liters of methane, I need to use my chemical equation to relate moles of methane or volume of methane to volume of water. So what needs to go on the top here? So I need the value in front of water to go in front of to go on the top. So that's what I end up with. So 2 liters of water for every 1 liter of methane. Okay. And then the volume of methane cancels out and we get volume of water. And then 6.04 times 2. I think that's 12.08. Do you agree? Okay. And then this has 3 sig figs, so this number will have 3 sig figs. So I'm just going to round to 12.1. Oh, thank you. It has a.
Wow.
Oh my goodness! It tells me I need to put the unit. So.
What did it do that for you in the test?
Yes. Oh, I put caps lock.
It would.
It won't
Yes.
warn you. So.
Yeah.
So sometimes it will warn you. Usually, if it warns you, you have the right number. It won't warn you if you have the wrong number. So if you ever get a warning, you have the right idea. Just like either your sig figs are wrong, or you don't have a unit like here. Yeah.
Will this sort of question ever be written as methane gas combust? Something like that?
No, not for us.
Just follows the oxygen reaction.
Yes. Yep. Yes. But yes, you are right. This is combustion. Perfect. Okay. Oh, sorry. Here. So that's from balancing. Here. So then I knew that I needed to relate water and methane because it. Yeah, this is just like a moles to moles problem from chapter 5, but it's liters to liters. Because it's a gas, I can use this relationship. Yeah. If I start with this much gas, then my equation will tell me the ratio of gas that I should produce. Yes. Okay, that's Avogadro's law. Next one is using the ideal equation of state, which everyone else calls the ideal gas law. Okay, ideal gas law is PV equals nRT. Okay, so I would write on my note card, besides having my equation, I would write what R is because it's in Alex, but I don't want to find it in Alex. That would make me nervous because sometimes I feel like it doesn't work for me. I can't find things in here when I need them. Okay, so let's see. Is this an SI unit? Nope. I think this one is unit conversions derived from SI units. We're looking for R. No, it's not. We're looking for constants. Where is that? Oh, here it is. 5 down. Fundamental constants. Okay. And we're using this top value for R. And another tip is, if you cannot remember what your unit should be for PV equals nRT, these are the units. You have to have liters, atmospheres, moles, and Kelvin. So that's a good. Oh my God. A good way to remember that. 0.0820 574 liters times atmospheres divided by moles times Kelvin. Okay, so I would put this, well, you can use your Alex calculator, but if you're going to use your own calculator, and I just like to have this number. So that's something I would put on my note card. All right. A reactor at -9 degrees Celsius evolves 510 millimoles of dinitrogen difluoride gas. Okay. So what do we have? We have the temperature, but it's not in Kelvin. So I'm going to add 273, and that's going to give me 266. I don't know. What's 13 minus 9? 5? Thank you. 2.
It's four.
I just believe you. So now we're right. Okay. Hopefully. So that's Kelvin. Maybe we'll have to check. Okay. So then we have what else do we have? 510 millimoles. N needs to be, this is N. N needs to be in moles, so we need to convert that to moles. So we have 510 millimoles. We're going to move the decimal 1, 2, 3 to get moles. Okay, the next thing is we're looking for the volume. You can assume the pressure is exactly 1. Oh, that's very nice. Thank you. Pressure is 1 atmosphere. So we have pressure. We have number of moles. We have the gas constant. That's always the same. R is just, we always have R. And then temperature, we have temperature. So we're just looking for volume. I'm going to divide both sides by pressure. So my volume equals nRT divided by pressure. Okay, so we have this 0.510 times by R. I'm going to run out of space, but if you keep track of units, that's R. Okay, if you keep track of units, then it will tell you if you have the right type of number. So that's helpful. Times 264 all over the pressure, which is 1. Great. So we've got 0.51 times 0.082. Oh, let's not type that in. Let's put in R. So if we go to this pi, this has all of the constants. We're using the gas constant, the second gas constant, times by 264, our temperature, divided by 1. Okay, well, 1 is fine. We don't have to divide by 1 because it won't change the value. Okay, and then because we have all of our units in the right, all of our numbers with the right units, this will be in liters. All of these have 3 significant digits. So 11.0 is our volume. We calculated everything else right. Okay, questions? Yes?
Anyone minds kind of a different?
Yes, there are at least 3 types of this question.
Okay, how do I find moles? There's one that doesn't give it.
It's just looking for atmosphere, but it doesn't give you moles.
Oh, okay. Do you have grams?
Yeah.
So if you have grams, so like for this problem, it gave us the formula. So we can find the molar mass. So let me write this. So this one, for example, this one is dinitrogen, difluoride. So we can find the molar mass by adding nitrogen plus fluorine plus fluorine. Okay, so whatever's in the formula, that gives me the molar mass. And then if you have the grams, right? So say we have 25 grams of this. So then I take my molar mass and I'm going to divide by my molar mass. So I don't know what. So 25, let's see. Oh, let's see. Where's my figure out table? So 2 times nitrogen plus 2 times hydrogen. This is the molar mass. Oh. So this is how many grams for 1 mole of this? For 1 mole. And so then we can find how many moles. So grams divided by molar mass gives you moles.
Teachers, could we please have the Rainbow Crew and the Asian American Club come to the deck for pictures? Thank you.
Okay, if that's you, go ahead and go. All right. let's come back to this one. There's a lot of types, but let's get through all of the types and then we'll come back. This one has some tricky ones, so we'll come back. Okay, next one is calculating partial pressure from a sketch. This one's not too bad. I like this problem. So this one, just make sure you count carefully. Usually it's 20 total, but make sure you do it right. Also, sometimes people forget to use the key. Red is oxygen, blue is nitrogen. Okay? Please don't mix them up. If you need help, like if you cannot see that, let me know. We can figure it out. Okay, so nitrogen and oxygen. So here, nitrogen is blue. So the first thing I'm going to do is just count the total. So nitrogen, I've got 1, 2, 3, 4, 5, 6, 7. And then oxygen, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. If this was the test, I would double check because I don't want to miss it. So it doesn't take that much time to double check. And then I'm going to add them up. That gives me 20. Great. The next thing is my mole ratio. To find that, I'm going to do 7 divided by 20 and get a decimal. 13 divided by 20 to get a decimal. So I'm just finding the fraction. What fraction is oxygen? What fraction is nitrogen? I don't have to put a decimal. I'm using my calculator. Okay. 0.35. 0.65. Okay, so these should add up to 1. So check. That's a check for you. The mole ratio should add up to 100%. Okay. The next thing is the partial pressure. So you just take your ratio and multiply it by the pressure in the system. So our overall pressure is 0.1 kilopascals. Part of that pressure is from oxygen, part of it's from nitrogen gas. So we just take it, multiply by 100. 0.65 times 0.1, not 100, 0.1. Okay, and then these should add back up to 0.1. Okay. Also, let's see. This value has 3 sig figs. So this table should have 3 sig figs. So 0.35. I need to add a 0 to have 3 sig figs. This one is 0.650 to have 3 sig figs. And then my partial pressures, I'm going to do oxygen first because it's in there. Times by 0.1. 0.065. Oh, that makes sense. And it should also have 3 sig figs, so I'm going to add a 0 at the end. So I can see what the pattern did, so I'm just going to type it in 0.035. These should add up to 0.1 because that's my total pressure. Check. Oh, this one. Thank you. This one needs. Thank you. Okay. Next one. The next one is hydrogen bonding interactions. I multiplied it by 0.1, yes, because that's the total pressure in the system. So I'm looking at the fraction of the fraction that is nitrogen gas and the fraction of the pressure that's contributed from the oxygen gas. Hydrogen bonding. Okay, there's 2 rules for this. This is something I might put on my note card. Let's just write them down and then I will close my window. Or I don't know if we need it. Okay, so there's 2 things that have to be true for it to have hydrogen bonding within the same compound. Nitrogen, let's see, there needs to be a hydrogen bonded to nitrogen, oxygen, or fluorine. There also has to be a lone pair on a nitrogen, oxygen, or fluorine. We need to know the structure of these. Oh, and some of them have a structure. Great. So this one, we're looking for, is there a hydrogen on a nitrogen, oxygen, or fluorine? There is right here. Hydrogen is bonded to nitrogen. Perfect. Then there has to be a lone pair on nitrogen, oxygen, or fluorine. Yes. So because both of these are true, it will have hydrogen bonding between is the same type of compound. Okay, the next one, between, we'll have, okay, if this one's yes, this one's yes. If it has hydrogen, if it has one of these to be true, that's all it needs to hydrogen bond with water. Okay, next one. This one I can look at if there's any OH groups, that's going to have hydrogen bonding because it has a hydrogen on a oxygen.
Is that what hydroxide is? It moves around and does its stuff?
Probably. That's a good observation. And then we have a lone pair on the oxygen. So yes, this will have hydrogen bonding within the same type of molecule, and it will also hydrogen bond with water. Okay, this last one, we need to know the structure before we can decide. So we have, a lot of these are just methane type molecules. We have a carbon with some hydrogens and some fluorines. Okay, so this one, we do not have a hydrogen on a nitrogen, oxygen, or fluorine. The hydrogens are bonded to the carbon. So this is not true. But we do have a lone pair on a nitrogen, oxygen, or fluorine. There's a lone pair on the fluorine. So this is partially true, yes. So it cannot hydrogen bond with itself, but only one of these needs to be true for it to hydrogen bond with water. So then this will hydrogen bond with water because of the lone pair on the fluorine. Okay, so we did 3 examples of that one. Let's keep going. The next one is identifying important intermolecular forces in pure substances. Okay, this is another one where we need to know the structures. So this one, oh, we had something similar. Okay, so we have this one. This is another methane type molecule.
What defines methane type?
Methane looks like this. So if it looks like this and something's substituted, then it's kind of like methane. Yeah, so then this one's called fluoromethane because we got one fluorine. Okay, so if it's a molecule, if it doesn't have any metals, then it's going to have dispersion forces. Okay, so we can go through, I like to just go through, okay, they're all molecules. Double check, sometimes on the test they throw in an ionic compound or a metal. Those cannot have London dispersion forces. Those are not molecules. Has to be a molecule. Okay, next one, dipole-dipole. So we are looking for something that's unsymmetrical for dipole-dipole. So dipole-dipole, we're looking for polar molecules. Dipole-dipole. Is it polar? And we're looking for something that's unsymmetrical. Okay.
So would water be symmetrical or not?
Not symmetrical.
It has the extra one.
Yes, it has extra lone pairs. Perfect. Yes. There's one side, we're looking for something. One side can have positive or negative charge, and water does that. Yes.
One side anyway.
Yes. So when you're looking at something that's methane type, so tetrahedral, as soon as you have one different group, then it's polar. If it has 4 identical groups, then it's nonpolar. As soon as you change one of them, or 2 of them, or 3 of them, then it's going to be polar, unsymmetrical. Okay. If it has CH or C, if it's like CF4, that's not polar. It's all symmetrical. Okay. All right. So this one has dipole-dipole because we have one group that's different than the others. So that fluorine can pull electrons. This one does not have hydrogen bonding because there's not a hydrogen on the fluorine. We just talked about water is polar because of the lone pairs. So it has dipole-dipole interactions. Oops. And it also has hydrogen bonding. There's a hydrogen on an oxygen, and there's a lone pair on that oxygen. Difluorine monoxide. Let's see what this looks like. So I think this is going to look something like this because oxygen. Oh. Let's see. I think it's going to look, so we know it's going to look something like this. chlorines don't usually like to have two bonds. Okay, let's do it like this. So we've got chlorine has 7 valence electrons, and there's 2 of them. Oxygen has 6 valence electrons, and there's 1. So this has 14, and this has 6. So that total we have 20 electrons. So I'm going to bond these together first, and I've used up 2, 4. So I've got 16 left. So I'm going to start putting around the chlorines. Okay, and then I've used 2, 4, 6, 8, 10, 12. So I've got 4 left. 4 left to show here. So I'm going to put them on the oxygen.
So it's equal, so it's not that.
So this one looks like water.
Oh, wait. Well, why'd you put it both on top?
Because I know it looks like water. So I can draw it like this, but you need to go back to chapter 4 where you think about the shapes. So because it has,
So it's got to be asymmetrical.
yeah, it has those lone pairs. So those lone pairs are going to stick out here. And it doesn't matter what side you pick, this side, this side, this side, this side. They're going to stick to one side, or they're going to point one direction, and the atoms are going to point the other direction.
It's like if you took off 2 of the hydrogen.
Yeah.
And those would tend to be lone pairs.
Yeah.
Symmetrical.
Yep, perfect. Yep. Yeah, and then these would be chlorines instead of.
So it's not.
So this one is polar. So if it is polar, then it has dipole-dipole.
It's polar, but no hydrogen.
Yes, no hydrogens, no hydrogen bonding. Yeah, so the shape is tricky, so you might want to view that. Okay, carbon tetrabromide, is that polar or not polar? So it has 4 bromines,
Sounds like it's not polar.
so it's equal. If it has 4 of the same group around the central atom, then it's not polar, so no dipole-dipole. Okay.
So any covalent molecule has dispersion force.
Yes.
If it's polar, it's got dipole.
Yes.
And if it's what those two we're going to talk about, it's hydrogen.
Yes.
Cool.
Perfect. Okay. Good. Okay. How are we doing? We're making it. Okay, next one. Predicting the relative boiling point. This one's a reasoning question.
Or is this one with the graphs or whatever? Oh, no, it's not.
Two more. The very last one is on graphs. Okay, so this one. When you're predicting the boiling point, this is what I would do.
Any students that are involved in the FCCLA and the Hope Squad, it is your turn for pictures on the deck. Again, that's FCCLA and the Hope Squad.
Okay, so first look for metals or ionic compounds. Those are going to have a high boiling point. The second thing I look for is things that I know are gases. If they're gases, they're going to have a low boiling point. So things like nitrogen, oxygen, NO, okay, CO2. I know those are gases, okay? The third thing I'm going to do is I'm going to look at the molecular weight. If it's big, then it will have a higher boiling point. The last thing I'm going to do is if they have the similar molecular weight, I'm just going to put molecular weight. If I have a similar molecular weight, then I'm going to look at intermolecular forces. Yes, specifically, a lot of them are just hydrogen bonding.
The greater intermolecular forces, the higher boiling point, right?
Yes. Okay, if it has hydrogen bonding, it's going to stick together more, higher boiling point. Okay, so let's look through here. The first thing I see is calcium and oxygen. Calcium is a metal. Oxygen is a nonmetal. That's an ionic compound. So that's going to have the highest boiling point. It's really hard to melt salts, boil them. Oh, and then I see a little molecule, CO. That's going to be a gas. I know that's a gas. Carbon monoxide is a gas. So that one's going to be the lowest, easiest to boil. Then I'm going to look at these two. I'm going to see if one's obviously bigger. So these to me look very similar. there's the chain is like a carbon, carbon, oxygen, carbon, oxygen, carbon. The hydrogen just kind of shifted. So these are very similar. The only thing that's going to be different for them is the intermolecular forces. So when I'm looking at these, is there anything obvious you see about the intermolecular forces?
D has hydrogen has
Good. Yes.
So C will boil easier.
Yes. You have this OH. Anytime you have OH, that's gonna have a higher boiling point. So that's gonna be the next highest, and then this one's gonna have weaker intermolecular forces. So it's gonna be easier to boil than this one. Okay. Let's get through all of them, and then if we want to go back through any, we can. Okay, next one is the specific heat capacity. This is another math question. We're using an equation to figure out how much the temperature change of a water bath. I'm going to erase this. Okay, so this one is this equation. Q equals M times C times delta T, or Q equals M times C times final temperature minus the initial temperature of the system. Okay, so this question we need to watch. What does the heat do? Okay, this is our heat. If heat is added, then the heat should be positive. If heat leaves the bath, then that needs to be negative to show that the temperature should go down if the heat is leaving the water bath. Okay, and just so you have a picture in your head, again, we have like something like this where we maybe have our water bath on a heating pad or a heating plate, a hot plate, and then our system is in the water bath, our reaction is in here.
So you're just saying water bath so that you can have a general, actual, real concept of it?
Yes, people do use water
So
baths.
it's just, the water bath is just a way for them to say this is how you have heat. So it's not just some random thing.
Yes.
But the water bath doesn't change the math itself. It's just there.
No. Yes. This is where you would see something like this. Yeah. Yes. Good. Okay. Yes. So this is, and we just have to decide, is the water bath adding heat to the system, the reaction, or is the reaction heating up the water bath? Okay, and you should be able to reason through that. So check your answer with what you think should happen. Did your temperature go up like you expected, or go down like you expected? Okay, so this one we have the water bath. We have the mass of the water bath. So this problem is nice because we don't have to convert anything if you understand how to do that. So Q is heat, M is mass. So I'm going to write the mass right here. 8.7 kilograms. C is a constant. They tell us that every time, but it's the same for water. If we're using water, that's the constant. It's different for every different material. There's a different substance. Okay, C, and then we are usually double check. All of the ones I've seen, we're looking for the final temperature, but make sure you're paying attention in case they change it on the test. Let's see. Yes, initial temperature is 34.6. We don't have to convert to Celsius because the temperature scales are the same for Kelvin and Celsius. So it's just like we're finding the difference. And then it says 111 kilojoules of heat flows out of the bath into the flask. So what does that mean? That should be positive or negative. Heating the flask. So, but we're looking for the water bath. Good, negative. Good. Okay. And then this is just an algebra problem. So I have these numbers multiplied together. These are like 3 numbers multiplied together. So I'm going to divide off the first 2 numbers. Oh, yes, go. Sorry. Okay, and then temperature final minus temperature initial. Okay. Oh, so if heat is leaving the water bath, our water bath temperature should go down. So we better get a smaller value for our temperature at the end. Okay. So negative 111 divided by 8.7 times by 4.18. Okay, so our temperature is going to go down by 0.3. So I'm going to take this and then that's negative. I'm going to divide, or not divide. I'm going to add my 36 to both sides. And that's going to tell me my final temperature. Plus 36.6. Okay, did my temperature go down? Did I do it right? No. Why did my temperature not go down? Oh, because I put 36. Should be 30. Oh, I wrote this down wrong. This should be 34. Oh my goodness. 34. Okay. Good check. 34. Oh. My temperature started at 34. I'm going to take off this much. And that's my new temperature. Did it go down? Yes, it went down. Okay, the other thing I need to look for is all of these have 3 sig figs. This 8.70. So that's how I'm going to know on the test how many sig figs you have. So this has 3. Run. Okay, sometimes let's do just jump to the explanation. See what we missed. Oh, let's see.
Suppose we also put the relevant one topic. We put 11.
Did I put 11 in the calculator? I think I said 11, and I meant 111. Okay, that will do it. Put the right numbers in. Okay, but we're getting, does that concept make sense? Okay.
As long as we use that formula, will it work every time? Like, will it be the same from?
Should be, yes. Double check? Yeah. So, yes, you should, like, for sure this equation, but also if you find the change in temperature and then just adjust the temperature, yes, it should always work. Yes. Okay. If you put the right numbers in, I feel like that's something that, I don't know why with this question, lots of numbers to keep track of. Okay, last question type on the test is identifying phase transition. So this is something I would put on my calculator so that I don't miss this. So you have your heating curve. On the left you have temperature. On the bottom you have heat added. Okay, and you have something like this. So on this first curve, this is where it's a solid. And then you add heat until it gets to this point. Then the temperature stays constant. While it's staying constant, what's happening? It's melting. Good. Melting or freezing point. Good. And this melting and freezing point has 2 phases. What are the phases here? Yes, good. So once everything becomes a liquid, then the temperature can increase again. So what's the phase here? Good. And then what's happening here? The temperature constant. Good. Evaporation, condensation, or boiling point. Good. Okay. And what phases do we have here?
Liquid gas.
Good. Liquid and gas. So if you're in a closed system, perfectly insulated, everything was perfectly scientific, then nothing would change temperature until everything turns to a gas. And then this phase curve is gas. Okay, this is just reading a graph. So please be careful. It's not that hard, but you need to make sure that you're awake when you're doing this problem. Okay, what is the melting point? So the first temperature constant is the melting point. The second temperature constant is the boiling point. So this one's melting point. So we just have to carefully read our graph, type in our numbers correctly. Great, 80. Double check. I don't know if we need a decimal. We'll put it in and see if it works wrong. The next one is, what physical state of X would you expect to find after 6 kilojoules kilojoules per mole of heat has been added? So here's 5, so 6. So what phase should we expect on this constant temperature curve? Liquid and solid. Okay. Okay, so this one, same thing. So if it ends up over on this curve, then this would be a liquid, this one would be liquid and gas, and this would be gas, and this would be solid. Okay, so that's something I would have on my note card, just make sure I don't do it wrong. Okay, so we've gone through all of the types of topics. We have 15 minutes left. Are there any that you need to go over up here, or do you just want to work and then I can wander around? Okay.